everybody, the purpose of this video is to go over section 3 of chapter 1 where we will talk about linear regression. First, we will talk about mathematical modeling, the ideas and the techniques behind it. We will discuss slope, and we'll discuss it from the perspective that slope is a rate of change between two quantities. And then we will discuss not necessarily the creation of regression analysis, but the application of regression analysis. In other words, if you actually have an equation which is a result of regression analysis, how can we actually use it? Okay, so what is mathematical modeling? Well, the strict definition of it is mathematical modeling is the process of using mathematics to solve real-world problems. Well, specifically, what does that mean, or how can you do that? And well, there are a number of ways. For example, if you have a phenomenon and you know the physics behind it, for example, the radiation of radio waves from an antenna, you pretty much know that it follows a spherical pattern. As a consequence, one equation for the received power density of an electromagnetic wave might be its transmitted power divided by the area of the surface area of a sphere, which would be 4 pi r squared, where r is the distance. Now, if it turns out that the radiation is very, very close to the ground, so that your receiver actually had it, so if your antenna is here and your receiver is here, and you get a direct wave, there it is, and a wave that bounces off the ground, which we call multipath, it turns out that your received power is going to be equal to your transmitted power times some constant, which you would need to figure out, divided by r cubed, and we call that a cubic power law model. Now, a lot of the models that you might be confronted with are models where we collect a whole bunch of data, we make scatter plots of that data, like this, and then from that data, we use regression to determine a line if the line is the best fit, or a parabola if a parabola is the best fit, or an exponential function if an exponential function is the best fit. But the basic idea behind this is that we construct a model, okay? Then we find a solution for that particular model, okay? And when we construct a model, that model might be y is equal to ax plus b. And for every value of x, we actually want to find solutions for y. And we want to interpret that model, i.e., does our solution make sense for the real-world problem at hand? If it does, great. If it doesn't, we might want to revise our construction, and we basically go around like this as we fine-tune our model. Okay, now, suppose that you have a collection of data points. So your data points look something like this. And these data points basically are very, very close to some linear equation. So once again, your data points look kind of like this. There might be a few blips, but for the most part, they follow a line. And this right here might be well, that's a pretty lousy fit, but suppose that's the fit for the line. Well, we would say that these data points are related, so it is related in some way, maybe not exactly, but pretty close to an equation where y is equal to mx plus b. Okay, so basically for a given m and a given b and a given xi, you can get pretty close to these to these particular points. Well, then we would say that this collection is linearly related, and it will have a slope. What would that slope be? Well, it's going to be basically the change in y, which you would call the rise, of course, or y2 minus y1, or whatever the difference between the difference between the y values of two different points, divided by x2 minus x1, which of course is the change of x, which we would typically call the run, where x1, y1, and x2, y2 are any 2 points on this collection. So we're looking at slope as the rate of change for the y value with respect to the x value. We can call this ratio not just the slope, but the rate of change of y with respect to x. Awesome. Now, if this rate of change is constant, if this basically is relatively the same for all values of x and y in your collection of data points, then we would say that there is a linear relationship. So if you had something where, once again, the points were pretty much like this, maybe there's a little bit of variation, it's pretty close to constant, we would have a linear relationship. Otherwise, the relationship between x and y is said to be nonlinear. For example, if your points looked something like this. Well, that is kind of pathetic, but that is obviously doesn't draw a line. It's more of a parabola, so this would be nonlinear. However, you can still find two values, say this value and this value, and you can actually still compute a rate of change. However, that rate of change that you compute would be an average rate of change of y with respect to x. Okay, so if your relationship is not linear, you may not be able to compute the slope, but you can still compute an average rate of change if you have values of y and x at two different points. Okay, and how can we use this? Okay, well, suppose that we have a car that's traveling northbound on I-85, and it enters South Carolina at 1 o'clock, and then 106 miles later, it leaves the state and goes into North Carolina at 2:15 p.m. And we want to find the average rate of change in distance over time, notice the vehicle speed. Now, first question is this vehicle traveling at a constant rate? We don't know. All we know is that it got into the state at 1 o'clock, and it left the state at 2:15. Okay, enter and then exit. For all we know, it could have stopped for a few minutes here, could have stopped for a few minutes there, it could have gone really fast here. It could have gone really fast here, probably slowed down because of all the construction in Gaffney here. We simply don't know. All we know is that it entered at 1:05 or 1 o'clock, sorry, and it left at 2:15. And that this distance is 106 miles. Accordingly, we could only compute its average speed. Now, if it was linear, then its speed throughout the entire thing would still be the average speed, would be equal to the average speed for the entire duration. But once again, we don't know that. So the average speed is going to be equal to the change in distance divided by the change in time. Well, the change in distance, we have it right here. It's 106 miles, piece of cake. Well, if the change in time is 1 hour and 15 minutes. Okay, now we don't want to work in hours and minutes. We either want to work in one unit or the other, and since we're dealing with our typical average speed, we actually might want to deal with this in terms of hours. And we know that 15 minutes is a quarter of an hour, so we can write this as 1.25 hours. Okay, so this is basically 106 miles divided by 1.25 hours. And if you knock that out in your calculator, you will have 84.8 miles per hour. Okay, here is another example that we might encounter. And this one has to do with computing doses for certain medicines. Here, the appropriate doses of medicine for both animals and humans are often based upon what we call the body surface area measured. Since weight is much easier to determine, all you need is a scale, than BSA, veterans tend to use the weight of an animal to estimate the BSA. And they apparently have very different relations for different types of animals. So the following linear equation expresses the BSA for canines in terms of weight. And we have A is equal to 28.55 times W plus 118.7, where A is the BSA in square inches and W is the weight in pounds. Okay, so the first thing that you're going to encounter is this question. Interpret the slope of the BSA equation. Okay, and in MML you are going to get four options. They will look something like this. Okay, and right now this is the slope of the BSA equation. All right, and the first point says, well, the change in BSA with respect to weight is negative 118.7 square inches per pound. Okay, does that make sense? No, because if you actually increase 1 pound, if W goes up by 1, then A is going to go up by 28.55, and this says negative 118.7. This is the y-intercept. So any answer that has the y-intercept in here has to be wrong. So this is out, and this is out. Okay, now, these two. The change in BSA with respect to weight is negative 28.55 square inches per pound. So they're saying here that if you go up 1 pound, you are going to reduce 28.55 square inches. That contradicts what this equation kind of implies, because if W increases by 1, then your answer is going to increase by 28.55. So this is out. There's only one option left, and there it is. Okay, let's take a look at Part B. Part B is, what is the effect of a 1 pound increase in weight? All right, well, this is a linear equation. Suppose W is equal to 0. All right, well, then A is equal to 118.7. What if W is equal to 1? All right, well, then A is going to be equal to 28.55 times 1 plus 118.7. Okay, notice the 1 pound increase in weight caused the BSA to increase by, you guessed it, 28.55. So the effect of a 1 pound increase in weight is a 28.55 square inches increase in BSA. As a matter of fact, we can also say that, you can also notice that 28.55 actually has units. And 28.55, their units would be square inches per pound. And this brings us to regression analysis. Now, what is regression analysis? It's basically the process for finding a function that provides a useful model for a set of data points. And typically this function is linear, but it doesn't have to be linear. It can be quadratic, it can be exponential, it can be logarithmic, and so forth. Now, graphs of equations are usually called curves, and regression analysis is also called curve fitting. And what we're saying here is we're actually going to try to find a curve that best fits the data according to some measure. And sometimes that measure is something called the least squared error, or the minimum squared error. We want to find a line or a parabola or an exponential function with the appropriate parameters so that the plot or the curve basically minimizes the error between the curve and the actual data points. And we call that minimum squared error or least squared error. And before we do that, sometimes it's usually helpful to visualize the data. And we do that by basically observing plots of data, and we call those plots scatter plots. And yes, this should be underlined, because that is something that I would like you to put into your notes, at least if you're using the guided notes. And these are helpful in deciding what kind of model best fits the data, whether it be linear or quadratic or whatever. For example, take a look at this scatter plot. Notice that here, perhaps these tend to show a linear relationship. As a matter of fact, perhaps a linear equation, something like this, might provide the best fit for the data. On the other hand, a linear equation would not be appropriate for a data set like this. Instead, perhaps a parabolic or a quadratic equation might provide a better fit, or maybe even an exponential equation. And now if you look at this one, well, in this particular one, a linear equation or a quadratic equation would not work, because this thing is kind of all over the place. In this particular case, maybe, actually, and it also depends on how this data is plotted, maybe something that we would call a sine wave, sine of x, or a sine wave, or a cosine wave with the appropriate parameters might provide the best fit. Since this chapter is focused on linear equations and linear inequalities, chances are the models that we will be looking at are linear. Now, we are not going to look at regression techniques. Instead, we are going to use regression models and use these models to produce certain values, and we're also going to focus on interpreting these models. And of course, that brings us to this example where we will be talking about diamond prices. And here we have that the prices for emerald-shaped diamonds from an online trader are given in this particular table. So, and the relationship is between weight in carats and of course price. And the linear model for this data, or a linear model, not the best linear model for this data, is going to be P is equal to 56,000 C minus 1,100, where P is the price of the diamond in dollars, and then C is the weight in carats. And the first thing that we want to do is plot the points on the graph, producing a scatter lot, or producing a scatter plot. And then we want to graph the model on the same axis. So we want to plot these points, and then we want to graph this line. And if you do, well, here are the points right here. And then here is a plot of the line right here. Okay? Now, it turns out that in MML you will not have to do this. However, what you will have to do in my math lab is to choose the correct graph from a collection of graphs. Okay? Now please keep in mind that P is equal to 5600 times C minus 1100. So the question here is, well, we already know that this is the appropriate graph, but assuming that we didn't, how will we deduce which graph is the correct one? Well, check this out. This one right here, the points are correct. I think they're correct. Yeah, they're correct. Okay. However, this is a regression line, and our regression line, and this is the apparent plot of the model, and this is just a straight line. This cannot be the graph of this equation, so this one is out. Here, notice that the scatter points are straight up. They are monotonically increasing. These are decreasing, as is the model. Well, if the slope is positive, we cannot be decreasing, so this is out. Okay, now as far as this one is concerned, here the points actually are correct. The points are good, but the model is not. How could you actually be sure? Well, notice here we actually have a crossing here at 0. Here we have the y-axis at 0.4, and at 0.4 this model is showing about 1500, or this line is showing about 1500. But if you actually computed this at 0.4, you would get something closer to 1100. So once again, this one is out. As a matter of fact, if you have a 0.4 carat diamond, then P, according to the model, would be equal to 5600 times 0.4 minus 1100, and that would be equal to 1140, which is pretty close to what this is, not what this is. So this obviously would, if we didn't know what we knew before, this would be the graph that we would select in MML. Now the next thing is we want to interpret the slope of the model. There's lots of questions like this. Now notice that this right here is the slope. So, and then once again, since this is the slope, and we're multiplying this by carats, it turns out that the units here are going to be $5,600 per carat. So essentially what's happening here is that as your carat increases, your price is going to be increasing at a rate of $5,600 per second. So with that information in mind, we can actually interpret the model slope. Is the change of price with respect to weight $100,000 per carat? The answer is no, because this is the y-intercept, so this is out. Is the change in price with respect to weight negative $1,100 per carat? The answer is no, because once again, that's the y-intercept. Is the change in price with respect to weight negative $5,600 per carat? No, because if you increase this kind of says that if you increase the size of your diamond, the price is going to go down. So this is obviously wrong. Since the slope is positive, this has to be the answer. And then, okay, two more things for this problem. Now we want to use the model to estimate the cost of a 0.85 carat diamond. Now remember, the model is that the price is equal to 5,600 times the weight in carats minus 1100. Okay, so we're just going to substitute 0.85 for C, and that means that P is going to be equal to 5,600 times 0.85 minus 1100. And if you compute it out, and if you knock that out in your calculator, which is really the only option you have, you would come up with $3,660. Okay, now the next problem is to use the model to estimate a weight of a diamond to 2 decimal places that sells for $4,000. Okay, so in this case, P is equal to $4,000. And we want to figure out what C is. Okay, cool. So we're going to substitute $4,000 in for P. And that's going to be equal to 5,600 times C minus $1,100. First thing that we can do is move this term that doesn't have a C in it to the other side. So we are going to add 1,100 to both sides. And of course, I'm going to do this vertically. These cancel. We will have 5,100, I almost said 5,500 by mistake, is equal to 5,600 times C. Okay, now we're going to divide both sides by 5,600. Once again, these cancel, and we will have that C is equal to 5,100 divided by 5,600. Of course, I can simplify this a little bit. This is going to be equal to 51 over 56. You don't really need to do that, but what the heck. And then if you did that math, you will find that the weight of the diamond is going to be equal to 0.910, so on. Okay, the third decimal place is a 0. That basically tells me that we don't have to round, and our answer is going to be 0.91 carats. Okay, let's move on to another problem. Here is example 4. Now here the table below gives data about the concentration of carbon dioxide in the atmosphere. Okay, and we have these values from 1995 to 2015. And somebody came up with a regression model. Here it is. Okay, where C is the concentration of CO2 and T is the time in years, with 1995 corresponding to T being equal to 0. Okay, cool. Once again, we want to interpret the slope of the regression line as a rate of change. Well, once again, this is our slope. It is positive 2.04. If that's the case, these can't count because these are intercepts. Now, this basically says that, okay, and what is this rate of change? Well, as T increases, then the carbon dioxide is going to increase at a rate of 2.04 parts per million per year. Okay, now it's not going to decrease, so this is out. It's going to increase. So that is our interpretation of the slope. And of course, once again, in MML, you will have these options. You just need to choose the correct option. Okay, next we want to use the model to estimate the concentration of CO2 that is in the atmosphere in the year 1990. Well, notice T equals 0 corresponds to 1995. 1990 was 5 years earlier, so this corresponds to T equal -5. As a consequence, our equation is going to be C is equal to 360 plus 2.04, and for T we want to substitute -5, so times -5. All right, well that's just going to be 360 minus 2.04 times 5, and if you knock that out in your calculator, you will have 349.8 parts per million. Okay, and this brings me to, yes, what you always like to hear, my last example. Okay, and this one is a forestry example. And here we have a figure, it's to the right, and shows the scatter plot for the white spruce trees in the Jack Haggerty Forest in Lakehead University in Canada. I have no idea where it is. But this is the scatter plot, And this is basically our best fit regression for the scatter plot. And this best fit regression, this is wrong. This should not be 0.34. I thought I fixed that. That should be 34. Is going to be h is equal to 1.8d plus 34, where d is the diameter at breast height, whatever that means, and h is the height in feet. Okay? And notice here that this is 1.8 times d. This is the slope. So 1.8d, 1.8, is going to have the slopes of feet per inch, because we are going to multiply it by d in inches and come up with feet. Okay, so first question is, yes, you guessed it, interpret this model, interpret the slope of the model. Well, once again, the slope is 1.8, so this should be 34 now, 0.34. But nonetheless, these are out, okay, because that's the intercept. Okay, once again, as the diameter increases, the height increases. Okay, as a consequence, this is out because this implies the opposite. So this right here is the slope. Okay, let's go ahead and take a look at part B. Part B is, actually this should be a decrease. Let me write that as decrease. What is the effect of a 1-inch decrease in the diameter at breast height? Well, if the diameter and breast height went down by 1 feet, then the height is going to go down by if the breast height went down by 1 inch, well, then the height is going to go down by 1.8 feet. Because think about it. If it went down by 1 inch, then the change in height is going to be equal to 1.8 times the change in height and diameter breast height, which will be negative 1 inches, and that's going to give you negative 1.8. So there will be a decrease of 1.8 feet in height. Okay, cool. What about part C? Estimate the height of a white spruce with a diameter of breast height of 10 inches. And then we want to round our answer to the nearest foot. Okay, well, that's just basically using this model where D happens to be 10. So we're going to have H is equal to 1.8 times 10 plus 34. Okay, that's supposed to be a point. That is going to be equal to 18 plus 34. And we can do that kind of math. That's equal to 52. And finally, estimate the diameter at breast height of a white spruce that is 65 feet tall. Okay, so in this case, H is 65 feet. And we want to find D. And I'm going to do this up here since I don't have much space down there. So we are going to have 65 is equal to 1.8 times D plus 34. Okay, once again, we need to solve for D. So we are going to use our tools for solving equations to do that. We're going to subtract 34 from both sides to get the terms without the variable on one side and all the other, and the terms with the variable on the other side. We're going to add vertically. These will cancel. Here we have 65 minus 34, which is going to be 31, and that will be equal to 1.8d. We are going to divide both sides by 1.8. These will cancel. We will have d, and that will be equal to 31 divided by 1.8, which is 17.2 inches. We want to round to the nearest inch. This is less than 5, so this rounds to just 17 inches. And that is all that I have for this particular section. If you have any questions, please feel free to contact me. This is Bob Oil, signing off.